All right, welcome to the Explainer. Today, we are going to talk about a really critical mindset shift. This is for every data scientist out there who's looking to level up their game. We're talking about moving from just doing a one-off analysis to actually building robust, engineered data workflows. This is really where data science smashes right into software engineering. So let's get into it.
So, let's say you're a data scientist. You're probably thinking about what's next, right? Maybe you've got your eye on becoming a machine learning engineer. It's a super common, really exciting career move. But what's the first real step you need to take on that path?
Well, it all starts right here. The absolute key is to change how you think about your analysis. You've got to transform it from, just a one-off script that runs once in a notebook into a repeatable, automated, and totally reliable engineering process. Honestly, that is the core of the ML engineering discipline, and that's exactly what we're going to break down today.
Okay, so to build that process, we have to start at the beginning with the foundation. And that is exploratory data analysis, or EDA, as you probably know it. Now, for an engineer, EDA isn't just about, finding cool things in the data. It's really the first stage of quality control.
I absolutely love this analogy. It is just perfect. Think about it. In carpentry, if you measure wrong, you waste wood, right? Well, in machine learning, if you skip a thorough EDA, you are creating a mountain of technical debt for yourself. It means you're going to waste, just massive amounts of time and compute power trying to fix flawed models that were built on data you didn't really understand in the first place. So, okay, the formal definition says EDA is this critical process of investigating data sets. But let's be real, for an engineer, it's way more specific than that. You're not just investigating, you're profiling your input. You are trying to understand its structure, its schema, all its weird quirks, and its statistical personality before you ever commit to building anything on top of it. And these goals, they are 100% tied to preventing things from blowing up in production. You're uncovering patterns to figure out if the problem is even solvable with the data you've got. You're hunting for outliers because, get this, a single bad data point can crash a live service or completely poison a model's training. And you're testing your assumptions, because a wrong assumption can lead to a model that just fails silently in the wild. This isn't just exploring for fun. This is serious risk mitigation. All right, so now you get the why. Let's talk about the how. We're going to start with the basic tools you probably already use, but we're going to look at them through a totally new lens, the lens of creating a systematic, repeatable health check for your data. We've all been there, right? You get a new data set, you load it up, and you're just staring at it. It can feel a little overwhelming. So where do you even begin? What's the very first, most systematic thing you should always do? You start by setting a baseline. So instead of just running df.info and glancing at the output, think about what you're actually doing. You're generating the first part of a data quality report. You're asking, what's the structure? Are there nulls? What's the memory footprint? Then, df.describe gives you that quick and dirty statistical summary. See? Together, these aren't just commands anymore. They're the first two sections of a standardized data audit that should kick off every single project. So once you have the raw numbers, you gotta see the patterns. And that means you have to visualize them. This is where visualization stops being just for analysis and becomes a true engineering tool. Using libraries like Plotly or Seaborn, it's not just for you to understand what's going on. It's about creating shareable artifacts that let your entire team, other engineers, product managers, you name it, quickly get the story of the data. Now look, doing all of this manually is crucial for building your intuition, but it just doesn't scale. It's not repeatable. To go from a craft to a real engineering discipline, you need force multipliers. And that means it's time to talk about automation. So here's the fundamental trade-off, right? Your manual, intuition-driven analysis, it's deep, it's focused, but it's slow. An automated tool, something like Y-data profiling, is the exact opposite. It is incredibly broad and unbelievably fast. We're talking one line of code to generate a whole comprehensive report that gives you an instant high-level overview. It's the perfect starting point. And this is the most important thing to remember. Automation doesn't make your skills irrelevant.
Not at all. It makes you way more efficient. These tools, they handle all the repetitive grunt work for you. They give you that 30,000-foot view of the whole data landscape, which frees you up to use your expert intuition to decide where you need to zoom in and investigate more deeply.
Speaking of investigating, let's dive into one of the most common hurdles you will ever face. I'm talking about a data quality issue you'll find in basically any real-world dataset: missing data. It's absolutely everywhere, and having a systematic plan to handle it isn't just nice to have, it's a non-negotiable engineering skill. Okay, first things first. Before you can fix anything, you have to actually see the problem. You've got to understand the structure of the missingness. Is it just random, or is there some kind of hidden pattern going on? A tool like Missing No is fantastic for this. It basically gives you a visual map of all the holes in your dataset, and that map is the critical first step to picking the right strategy to fix it. So once you can see the problem, you've got a playbook, and it's all about clear trade-offs. Your first option is to remove it. Just delete the rows or columns. It's the simplest choice, but it can be risky. If that missing data isn't truly random, you could be introducing some serious bias. Option 2, impute. This means you fill in the gaps, maybe with the mean or even a simple model's prediction. This keeps your data, but it might artificially shrink its variance. Then there's option 3, indicate. You actually add a new column that just flags whether the data was originally missing. This is cool because it lets your model decide if the fact that the data was missing is a predictive signal in itself. Picking the right path here, that's a core engineering decision.
Okay, we've talked about manual inspection, we've talked about automated profiling, and we've got a game plan for missing data. Now, let's pull all these techniques together into the engineering framework we've been building towards this whole time, the MLOps mindset.
This workflow right here, this is the heart of engineering your analysis. First, you build your foundation with manual analysis to really get your own intuition. Then, you accelerate with automated tools to get that fast big picture overview. Based on what you find, you triage the most urgent problems, like those missing values we talked about. And finally, the most critical step of all, iteration. You turn this whole process into a standardized, version-controlled, repeatable script. It becomes the official first step in any modeling pipeline you build. That is the difference between just doing analysis and actually engineering a solution.
So, I want to leave you with this challenge. The next time you open up a Jupyter notebook, don't just see it as a temporary scratch pad. See it as what it really is, the foundation of a product. It's the very first component in a potential production system. And I'm telling you, that shift in perspective, it changes absolutely everything. So the only question left is, how are you going to engineer it?